Right. Quite a lot of attendees today. We'll give it one more minute, ladies and gentlemen, and then we'll kick things off. Right. I would say, without further ado, ladies and gentlemen, let's get started. As you can tell from the site, today it's all about smarter mold designs with integrated fill, pack, and cooling simulation in the cloud. So good afternoon or good evening from wherever you're joining us right now. Also to all the injection molding innovators and digital manufacturing visionaries. Today, as I've already told you, we're tackling one of the biggest challenges in plastics engineering. How do you ensure manufacturability, cycle time efficiency, and the highest part quality without endless trial and error on the shop floor? Traditionally, fill pack analysis helps optimize part design and gate runner locations in early development stages. But let's be honest, that's only half the story. True process reliability requires going further into the cooling domain, where thermal management decides both quality and productivity. And that's why IANUS Simulation and Maya HTT join forces to bring you a cloud-based end-to-end workflow where fill, pack, and mold-aware cooling come together seamlessly. A single environment where you can simulate smarter, make informed design decisions earlier, and cut down on costly iterations. And guiding us through this journey are two leaders who bridge deep engineering know-how with cutting-edge innovation. Number one, my dear colleague Marius Dörner, Chief Business Development Officer at IANUS, a plastics engineer by training and process innovator by practice. Marius has spent his career translating complex material behavior into actionable simulation insights. His focus today, how generative AI and advanced modeling make it possible to predict optimal sensor placement and heating strategies, ensuring uniform temperature profiles without endless experimental loops. Second on the list, Christopher Blake, Director of New Product Development at Maya HTT. Chris brings 17 years of experience across aerospace, automotive, electronics, and beyond. From running high-fidelity CFD and thermal analyses to leading enterprise-scale software and PLM projects. Today, his mission is to explore cloud simulation, AI ML, and simulation-driven design as the next frontier of efficiency and scalability. At the end of every session, as always, we'll open the floor for your feedback with a quick interactive poll, and you can ask all of your questions in the chat. So get ready to explore how IANUS and Maya HTT are redefining injection molding simulation, and I'll hand over to Marius. The stage is yours.
Thank you, Josef. Yeah, nice introduction. Also, a warm welcome from my side. Before we really dig in, I want to bring really also a short few points, what's in for you today, so that you say, okay, it's worth to invest these 30 minutes of webinar. It goes all around mold making, and mold design. So today we really want to show you how with our different parts and software and how they together can improve for you the, for example, filling simulation with Strömungsraum for even very complex parts, but also how the cooling augments the fill and pack for better results. And even with SimForm channel recommender can then optimize the overall cooling layouts. That's all. And then in a cloud workflow, which speeds up your simulations at the end. And that will show you how, with this combination, with this partnership of SimForm and Strömungsraum, you will improve your part quality and your cycle time at the end. So I think that's worth it. So let's have a brief look how we structured our talk today. We are right in the welcome, obviously, and then afterwards we will show you a short overview about IANUS and Maya HTT, just a few slides, what we're doing, what is our mission, to dig then into the different packages of Strömungsraum and SimForm, what are the differentiators of the software and what's the vision at the end of our workflow. Bring it into a demo so you see what we are doing, how easy it is, and what brings you for a benefit at the end, ending with the Q&A. If English is not your native language and you want to turn it on live captions, that's also possible. Like seeing here right in the picture, the 3 dots in Teams, you can turn on live captions to whatever language you want. So that as an introduction, let's now really look into the first point, the overview, and I will just start because I'm talking right now. So a short overview about IANUS simulation. What are we? We are at the end a software as a service company, and our idea is really to bring everybody to be able to simulate. So really bring simulation to every small, big, medium company because we make it very easy. That's the thing we were focusing on. Make easy simulations, start simulations with just a few clicks without being an expert in simulation, without buying huge software packages or something like that, just in a really easy way. And that's what you also gonna see today. We do this with more than 100 employees. Because we do automated simulations, quite many per year, like 3 million. And what's also important, we don't do this not only for injection molding, but also for a wider space on plastic processing, for centrifugal pumps, and for many other types of simulation, because we have there a really great network where Maya also belongs to. So that just with a few words about IANUS. How do we do this easy simulation? Also there, I want to bring in a short info to Strömungsraum itself, because it's a web-based platform. You can go on it from any device you have and really make it quite easy. Just upload your part you want to simulate. In this type, it's a profile die for plastic extrusion. You just upload it, click the plus, input a few parameters you need, and at the end, that's all to start a simulation. You wait a few things, drink a coffee, and at the end, you can have a look at the results. And that's what our aim is, always to be easy and to be precise. And just a few words from customers we have, feel like BBM, who do blow molding simulation, VK, who do plastic profiles, or Evicon, they are from the injection molding side. They do hot runner systems, all of them saving resources due to our simulation. And yeah, that's why we are doing this. And that's a short overview. And with this last words, I would hand over to Chris, who talks a little bit about Maya HTT.
Thanks, Marius. Yeah, so nice to meet everyone. My name is Chris. I'm actually calling in from Canada, where I'm based. So just as a brief introduction to my HTT, we're an engineering solutions company. We specialize in, similar to IANUS, in software development, but also in engineering services and partner sales. So we've been in business since 1982 and have grown to employ over 250 experts in Europe and North America. I'd say that our biggest differentiator as a company is our ability to combine the expertise we have in developing advanced simulation software, our team of industry-focused engineers and architects, and our portfolio of partner products, and our ability to combine those into a custom solution that really benefits our customers and clients in improving their workflows. So a few years ago, just make sure, there we go. Maya engaged with several customers in the plastic injection molding industry. One was an OEM, one was a mold maker, and then there was an extensive project with a hot runners company. And we discovered that there was a need for fast and convenient, yet still insightful simulation software, specifically for mold cooling. Now, our core expertise originally was in heat transfer. We've now grown to offer all sorts of different simulation solutions, but our heat transfer background allowed us to develop SimForm, which is an entirely cloud-native simulation platform that is used by part designers, tooling engineers, and mold makers to improve the quality of their parts and improve the efficiency of their plastic production processes. We do that by providing easy and fast simulation capabilities that you can make part of your design workflow. So basically to drive your designs using simulation. So SimForm is easy to use. You can set up and run a cooling simulation in just a few minutes. And you can even include the full geometry of your plastic injection mold. We can simulate the effects of the cooling lines, the different material selections for your inserts, for your core pins, for your sliders, etc. And with our generative design tools, we can even show you where to route your cooling channels to get the most optimal process. So here are some positive feedback that we were receiving from our customers. I think the most interesting one is from Thibault in the top left. They've successfully made SimForm cooling analysis a consistent part of their mold designs. They outsource all of their mold designs, but have all the engineering capabilities in-house so that they check and validate and iterate on all those outsourced designs by using SimForm as one of their key tools for assessing the cooling performance. So I'll send it back to you, Marius, just to keep going into a deeper dive.
Perfect. Thank you, Chris. Yeah, let's now really deep dive a little bit more into the packages itself. So I will just start with our Strömungsraum for injection molding and with our credo. I told a little bit also before, our credo is always to be easy, but nevertheless be very precise. That's often something which counteracts. Our mission is really to bring these both together. So really to have the ease of use. So you don't have to be a specialist in simulation to start such simulations. You can start it just with a few clicks. And since it's automated, you have also always very good comparable results because you don't have some different inputs from different users. In the meshing, for example, it's all automated. And so it's all very good comparable. And so you can drive the right decisions after that. To get the right decisions, you obviously need also a good precision in the simulation because we don't want to make just colorful pictures. We want really to have detailed results. And for that, we have invested much time into an high quality 3D measure, which I will show you also afterwards. So we can create very good meshes for the simulation, even for complex parts, and bring them in a reasonable time also to a solution because we are using high performance clusters where the simulations then are running out. So you don't need any hardware by yourself, just something where you can browse with in the internet. That's the next point. So it's cloud-based to our German high performance clusters. You can access this from everywhere you want to, also from a smartphone in a way. You could start a simulation from a smartphone if you want. And at the end, it's also completely automated, also from the results side. So you get always the same PDF report adjusted to you, to your results. But you can dive deeper into a live viewer if you want to, and that's what we will show later on in this talk. So what's the overall process that you want to simulate with Strömungsraum? It's really very easy. You just take your part you want to simulate, you upload it into Strömungsraum, enter a few values. The simulation will automatically run on the clusters, and this time you can do something else. For normal, we have many things to do besides simulation, so let the simulation do the PC. And at the end, you can evaluate everything also automatically with a report, but also with live view. That's all in the full automated circle in the cloud. We have also some optional services, tool design, part optimization, and feasibility analysis if needed, but that's totally optional. So how's the simulation running through good automated? It's really because we invested much time in a good measure, which automatically generates high quality 3D meshes. My boss always says high quality comes from high precision. That's somewhat true. So you see, for example, we really invested much time to make it possible to really get a feature recognition also just from step files. Because step files at the end are also more or less point clouds. And you can see that we see, okay, in these areas, there are small circles, there are radiuses. At this, we will do a higher precision meshing, while in the areas where there's more place, we do a little bit coarser meshing instead of a typical TED meshing some competitors do. Also there, for example, you see that this also enables us to really have a good resolution at imprints, for example, or at small rips in this kind, which you sometimes with the TED dominant meshing just cannot see at the end. So we're really looking that we there get a high quality mesh to get a really precise filling. And to get this precise filling, we do this also as a two-phase simulation. So it's really simulating the melt, breathing air out of the part with a 3D mesh at the end. And that's what brings us to the good results we want to deliver to you as a possible customer. That is a short intro to Storm. Let's hand over to the magic SimForm does.
All right. You're going to see a lot of commonalities between our softwares, which is really, really interesting and exciting. So SimForm similarly is known for its accessible user interface. You have on the left the simulation jobs for a given project. On the right, just the material properties. Middle is your CAD that you interact with. But probably what's more interesting to know about is the technology which is at the core of SimForm, and that's our thermal solver. So our thermal solver employs a meshless voxel technology. So that means that we discretize the domain using these cubic cells that you're seeing on the right-hand side there. And it's on those cells that we compute the temperatures. Now, because this mesh, in quotation marks, is not required to conform to the underlying geometry, it is virtually failure-proof in the face of complex or imperfect CAD. So this really alleviates the meshing burden from the end user. It's fully automatic, transparent. The user doesn't have to do any meshing. To capture the necessary details, however, we have an automatic refinement algorithm that refines the mesh as you get closer and closer to the part boundaries. And there's also a target resolution that's automatically selected in order to ensure enough resolution on the areas of important detail, like through the thickness of the plastic part, where there can be significant temperature gradients. Now, the thermal solver itself takes advantage of that voxel mesh to perform most of its calculations on graphical processing units or GPUs, as opposed to the typical CPU. So these calculation steps include the meshing step that I was talking about before, the cooling line construction and extraction, and then the actual solve of the transient thermal equations. All our calculations are done on A100 GPU machines that are hosted in Azure Cloud. And because of the extreme parallel nature of these calculations, we can support very large models. The largest one that we have seen so far is 190 million cells, which corresponded to, it was a compression molded part about 3.5 meters in length. So very large. But for a typically sized mold, you can encounter run times that are in only about 15 minutes. That's the full transient simulation of the cooling process. So that really enables simulation-driven design workflows like I was talking about before. You can have simulation accompany you as you're doing your design process and iterating. Whoops. All right. Hit the button by accident. On the topic of cooling channel construction, other tools often require clean three-dimensional CAD to represent the channels so that they can be meshed, or at least some sort of centerline or polyline representation of the channels. Again, our thermal solver relieves that burden off of the end user. We extract cooling channels directly from the voids within the mold base. And we also handle complex features like baffles inherently within the solver. You don't need to model them explicitly. We capture the heat transfer effects of those automatically. And then on our GPU, we algorithmically extract all of the center lines and calculate the path of the fluid flow through the network of cooling channels. We calculate how much flow is going through the channels, and then we calculate the cooling capacity of each. So basically how much heat is removed from each channel, and we report it back to the user to get an assessment of how efficient the process is going. So hopefully you guys can appreciate why it is that IANUS and Maya have teamed up. I think it's natural to have this partnership come in place because we share a common vision. It's to make simulation accessible and fast in the cloud and really enable those simulation-driven workflows, especially for the plastics injection molding industry. The shared use case that we're working on is to help users iterate both their part and mold designs earlier in the process to help drive that design, rather than leaving simulation as a validation step later in the process, often when it's too late or at least too expensive to make any design changes, especially to the part, but even to the mold if you're about to cut metal, for example. So we're doing this by combining our capabilities. So SimForm can provide more realistic boundary conditions to the fill and pack process. We can provide the distribution of mold temperatures, and vice versa. Stormix can provide back the temperature distribution within the melt at the end of the fill pack process to give better initial conditions for the resin in the cooling simulation. And then we can send back differential shrinkage results for even more accurate warpage prediction. Together, we're going to be able to provide a much deeper set of insights. You get the fill patterns, the weld lines. We provide an estimate of the cycle time, the cooling capacity, mold temperatures, and then you can assess what risk of warpage and what defects are going to occur as a result of the entire injection process simulation. Of course, our vision is to provide all of these capabilities in a more seamless cloud-native workflow. So combining the advanced fill and pack, the cooling, and the warpage analysis with the same ease of use and simulation speed that we've been describing throughout this presentation. So Marius, you're gonna do a demo now, I think.
That's true. So let's just have a look how easy this really is. I've brought a short introduction demo here with me. So it's really when you go to Zimod.de, that's the domain at the end with every device you want to, you will hand over to a dashboard where you can see what are your latest simulations. They are in this case done. You see this check and you see your latest 3D models where you can start a simulation right away from. So let's imagine you want to do a new simulation, just upload your part. Let's take the controller, click on a plus, and then you can write start. So you want injection molding in this case, you want some material to simulate, you see the temperatures are already there, and then you want just to simulate all packing, warpage, injecting, all of this, just pick it on and say where is the point where my injection goes in, and that's all. All the things you need to know to start, you can double check if it's all right, and then click start simulation. It goes to the clusters and starts running. After time, you see now it's checked. You can click it again and you get your results back, like a PDF file, a report, or live viewing. So the PDF file, you see it's really convincing all the different stuff like fill time, temperatures, melt front temperatures, pressures. All this stuff is in there for every simulation you do, like the same. But if you want to dig deeper into it, you have directly in the browser also this live viewer where you can see the pressure in the filling, temperatures over the different stages. Where do I have possible weld lines? Really to see where they are in your part or what's the fill quality overall. So at the end, really, also you see there that's really the easy workflow. You can start simulations right in a minute, not more, and get your results as easy back as you start a simulation. So that is a really fast demonstration of Strömungsraum. And I think, Chris, you have something like that also.
Indeed. So yep, it's in full screen. So I'll show you a quick demo of SimForm. Actually, I'm going to focus on our generative design workflow. So here I create a channel recommender job. My CAD is there. And I specify a few manufacturing constraints, mainly the distance that I'm allowed to have my cooling channels from the surface of the plastic. The result I get are the recommended cooling regions, which are the regions of highest cooling demand and where you need to route your channels. And one of the other results is an estimate of the temperature that results from that recommendation. But then I can use that recommendation in an assessment job where I can overlay those recommended regions on top of my CAD and actually use those as anchor points for actually building up a cooling layout, hypothetical cooling layout or experimental one. So I can do all this directly within SimForm. I don't have to leave and go to my CAD system. I can add more complex cooling features like baffles like this. And then once I have all of my cooling network built up, my conceptual design, I can put a basic mold block around it, pick P20 mold steel, and run an assessment simulation. The initial result I get is called the freeze time, which is a contour plot of locally how long it's going to take for the part to solidify enough to be ejected. You also get an overall estimate of the cooling cycle time. And then I can go back through the history of the cooling period just to understand when the hotspots develop and see if there's any opportunity for process improvement. And again, all that's happening directly within our cloud app and using the hardware that is accessible within the Azure cloud. So very brief demonstration. Obviously, we can show you more at a later time. I'll let you speak on this, Marius, to finish things off.
Yeah, perfect. Thank you, Chris. Yeah, we can speak on this in more detail later time. Later time could possibly be the cave in October. So if you want to experience Strömungsraum and SimForm live there, just come to our stands in the different halls. You see it at the bottom. Also, we have some little gimmicks there if you visit our both stands. So come over and we can talk about it in detail more. And I think that's it for this webinar today. And I will hand it back to Yusuf. So if you are in any questions, he will manage.
Absolutely. Christopher and Marius, thank you so much for the nice presentation. Let's hop over to the questions from the audience. Question number one, what inputs and criteria are used to generate the cooling channel recommendations in SimForm? I'll hand that over to Chris.
Yeah, so I went over really quickly there, but basically the inputs you need are the CAD of the plastic part that you're interested in and a few of the manufacturing constraints. So what is the temperature of your chiller water? How close, given the mold steel selection, that you can get the channels to the surface of the cavity and core, because this is going to be ultimately 3D printed. If you're going to do a conformal cooling design, there are usually criteria on how close you can get to maintain that structural integrity of the mold inserts. And then what we actually do is a generative design algorithm. It's an optimization loop that tries to minimize the deviation, or rather the variance in the temperatures on the surface of the part. You try and get it as uniform as possible, given those constraints and the cooling time that is trying to be achieved. And that is to minimize the amount of warpage that could be experienced by the plastic part. And then we report back the areas of highest cooling demand that are where you need to route the cooling channels. So hopefully that answers the question.
Excellent. Let's give the next question to Marius. How long is a typical filling simulation running? Is material data provided?
Yeah. So typical filling simulation, always depending on the part you have, how complex it is, obviously. The example I showed you, it's like an hour really from starting a simulation, inclusive meshing simulation, and getting all the results for all the stages until the warpage. So filling itself, when we focus on this question, is around half the time. So like 30 minutes in this case, if you just want to see the filling, for example. It can go up, obviously, if you have bigger parts. It can be then also when you simulate all the stuff like 3 hours. But the important thing is there, since it's on the HPCs, on the high performance clusters, you're also available to start 5, 10, 15 simulations at once. They will run in parallel and you get the simulations back. So that's also important if you are in the first stage of building your part and you have different designs you want to try against each other. You can run them all seamlessly in parallel and get all these simulations then back in the same time, like just one simulation. Second part, I think, was about the materials, when I'm right. Yes, okay.
Yeah, the material. Yeah, correct.
Yeah, we have a material database lay behind that's with around 5,000 thermoplast materials. You have there the MFR values. What is it for a material? Do you have fibers or other fillers in there that's directly integrated into Strömungsraum? So you just can pick it up.
Excellent. Thanks, Marius. Next one for Christopher. What is the typical runtime encountered with simulations in SimForm?
Yeah, same question.
Quite similar, yeah.
Yeah. Yeah, that's one of the things we really focused on, like I was mentioning, it was to try and make simulation easy and make the workflow from transitioning from CAD over to simulation as seamless as possible. We encounter runtimes that are in the order of 15 minutes. So I'd say between 15 and 30 minutes for medium to large size molds. Again, it's being done in the cloud using those GPU machines that are hosted in Azure. So, like I said, we can take advantage of the highly parallelized nature of the calculation to get those types of runtimes.
That covers it, Christopher. Thanks a lot. Then we have another question. What is different about your offering compared to, say, Moldflow or Moldex 3D?
Yeah, very good question. I think we're definitely in the same space, like in the same industry software offering. I think what differentiates us is the ease of use and the speed of simulation. And I'm actually talking on behalf of both of our companies now, not just SimForm. Our whole reason is to, like I've been saying, make simulation accessible to designers and engineers and not focus on the CAE specialists. So by having that easy to use workflow, they're more likely to use it and more likely to drive their designs using simulation. And so that's really what I think differentiates us. And the fact that now we're partnering together to offer the entire simulation process flow, it makes the solution for designers and engineers that much more compelling.
Would underline that to 100%.
Excellent. Again, guys, thank you very much. Excellent presentation. If you want to learn more about MyHGT and what they're offering, go to myhgt.com. And for IANUS, you have IANUS-simulation.de. We'll be covering more questions or webinars actually around the topic of GPU accelerated computing, AI, ML, and data-driven simulations in the future. Thank you very much for attending, and I'll see you guys in the next session. Have a good one.
Thank you.
Thank you very much.
Bye-bye.